So, if you were to list out the absolute essentials for human survival, you'd probably rattle off the physiological non-negotiables pretty quickly. Air, water, food,
Yeah,
shelter.
the absolute basics.
Exactly. But when you look at the foundational networking principles we're diving into today, there is a really compelling argument that another fundamental need sits right below those physiological ones.
Oh, absolutely. The need to communicate.
Yeah, exactly. The human need to interact, to collaborate, and just communicate is practically on par with our reliance on water and shelter.
It really is.
So, welcome to today's deep dive. We are unpacking a foundational IT source today, specifically the CCNA Introduction to Networks Module 1, which is all about networking today.
It's a great module.
It is. Our mission here is to really demystify the invisible digital architecture that connects our world. We want to give you a shortcut to understanding the exact infrastructure that is quite literally powering your daily life.
And there is a lot going on behind the scenes that we just take for granted.
Oh, 100%. So, okay, let's unpack this. Because this isn't just a dry breakdown of, like, cables and hardware. It's a real exploration of how networking technologies have systematically erased physical boundaries.
Right. Creating these global communities that just operate completely independently of geography or, time zones.
Yeah. And the implications of that boundary erasure are massive.
They are, especially when we look at human productivity.
Yeah.
I mean, the architectural shift toward the cloud is just a perfect example of this.
Right, because we aren't just talking about a remote hard drive where your backups live.
No, not at all. We are talking about decoupling productivity from a physical location entirely.
Which is wild to think about.
It is. Because whether you are commuting on a train or, sitting in a localized office or even standing on top of a mountain with a satellite uplink,
Right.
the network architecture allows seamless, on-demand access to distributed computing resources, data, applications, all of it.
So you basically have the exact same functional power in your pocket as you do at a corporate workstation.
Exactly.
Mm-hmm.
But to understand the mechanics of that untethered productivity, we have to look at the root actors making these connections happen in the first place.
Okay, the cast of characters, basically.
Yeah, exactly. So at the foundational level of any network design, we have the hosts, or what they call end devices.
Okay. And these are the nodes participating directly in the communication flow, right?
Right. And traditionally, these hosts operate on a really strict client-server architecture.
Right, I've heard that term.
Yeah.
So you have these heavy-duty servers provisioned with specialized software and hardware to provide resources.
Yeah.
Whether that's like serving up web applications, hosting massive relational data presses, or just managing corporate email routing.
Exactly. And then on the other side, the clients are the endpoints initiating requests to consume those resources.
But wait, I mean, if I'm looking at this, that traditional model sounds really expensive.
Oh, it is.
Right, because deploying dedicated servers requires significant investment. You need enterprise-grade hardware, cooling, power, specialized IP personnel.
Yeah, the friction often comes down to capital and complexity. For smaller scale operations or highly decentralized environments, that overhead is just really difficult to justify.
So why don't we just connect all our computers directly to each other? Skip the server entirely.
Well, you can, and that's why peer-to-peer or P2P networking remains a persistent alternative in specific use cases.
Okay.
In a P2P architecture, that expensive middleman server is entirely eliminated. Every single device on the network is configured to function as both a client and a server simultaneously.
I mean, I can see the appeal of P2P from a purely financial perspective.
Sure.
If I have a small satellite office and I just need to share a local printer or, a local storage drive among a few workstations, a decentralized P2P setup avoids the cost and the configuration nightmare of standing up a dedicated server rack.
Right, and the initial deployment of P2P is incredibly frictionless. It's fast and cheap.
But there's a catch.
A huge catch.
Mm.
The architectural trade-offs are severe, which is why P2P never scales to enterprise levels.
Because there's no centralized boss.
Exactly. Without centralized administration, you have no unified security policy. Every user basically becomes their own network administrator.
Which sounds like an absolute operational nightmare.
It is. Furthermore, there's a massive performance penalty.
Oh, really?
Yeah, think about it. If a workstation is acting as a client for a user's local tasks, but is concurrently acting as the server handling file requests from like 5 other nodes on the network.
Oh, right. It's doing double duty.
Exactly. The CPU and memory overhead on that single machine just skyrockets. The host device simply bogs down under all those concurrent connection requests.
So P2P is really just a localized Band-Aid, but it completely falls apart structurally if we try to scale it up.
Spot on.
So to build a robust global infrastructure, we clearly need dedicated systems to manage the traffic. I mean, we have the end devices where the data originates and terminates, but how does a message actually travel from a smartphone to a server halfway across the world?
Well, they don't connect directly. They require a sophisticated layer of what we call intermediary devices.
Okay, the middlemen.
Right. Those intermediary network devices are the true workhorses of the internet. They're responsible for regenerating and retransmitting data signals.
Okay.
They maintain information about what pathways exist through the network, and they notify other devices of errors or communication failures.
I always find it helpful to visualize this intermediary layer as a massive public transit system.
Oh, well, yeah, that.
Yeah. So like a switch operates like a highly efficient local traffic cop. Its entire job is to memorize the physical hardware addresses of the devices directly connected to it and rapidly switch traffic between them within the exact same local area network.
Right, it keeps local traffic localized.
Exactly. But then a router acts more like an international airport hub.
Yes.
A router doesn't care about the physical hardware addresses. It reads logical IP addresses to connect entirely different networks together. It makes those complex pathing decisions to direct traffic across the wider internet.
That is a perfect analogy.
Yeah.
And building on that transit idea, we also have wireless access points.
Okay, where do they fit in?
They basically function as the localized boarding gates. They aggregate wireless signals and bridge them onto the wired network.
Ah, got it.
And crucially, we have firewalls.
The security guard.
Exactly. They are the border security checkpoints. They don't just route traffic, they actively inspect the data payloads and connection states against a really strict set of security policies.
Dropping malicious or unauthorized traffic before it can even penetrate the internal network.
Exactly.
Okay, but here's where it gets really interesting for me. We can map out these switches and routers all day, but they are utterly useless without the physical layer.
Right, the actual roads.
Yes, the actual network media carrying the data. Looking at the engineering principles in the module, there are 3 primary physical mediums, and they each deal with entirely different laws of physics.
Yeah, it's fascinating. First up is copper cabling, which is the backbone of most internal local area networks.
Because it's cheap.
Basically, yeah, copper is ubiquitous because it's relatively inexpensive and it's easy to terminate. It functions by encoding digital data into electrical impulses.
Okay.
The networking hardware essentially modulates voltage states over the copper wire to represent binary ones and zeros.
But there's a downside to electricity, right?
Huge downside.
Yeah.
Electrical signals are highly susceptible to attenuation.
Which means the signal degrades over distance.
Exactly. And it's also vulnerable to electromagnetic interference, or EMI.
Like what?
Well, if you run an unshielded copper network cable too close to fluorescent lights, or, say, an elevator motor in a building,
Oh, wow.
the ambient electromagnetic field from those machines can literally corrupt the data stream inside the copper wire.
Which is exactly why we rely on fiber-optic cabling for high-bandwidth long-haul transmission, right?
Precisely. Fiber completely abandons electricity.
Uses light instead.
Yeah, it encodes data as rapid pulses of light firing lasers or LEDs down microscopic strands of extremely pure glass.
That's just wild to think about.
It is. And because it relies on the total internal reflection of light, it is entirely immune to that electromagnetic interference we just talked about.
So no elevator motors are going to mess up a fiber connection.
Right. And it can push massive data payloads across oceanic distances with almost zero signal degradation.
Okay, so that's copper and fiber. What's the third medium?
The third is wireless. And this one abstracts the physical cable entirely.
Right.
It encodes the binary data into complex patterns of electromagnetic waves broadcast through the air using specific radio frequencies.
Which provides the ultimate mobility, obviously. But I imagine it introduces its own challenges.
Oh, definitely. Primarily shared bandwidth constraints and a high susceptibility to atmospheric or physical interference, like walls or even heavy rain.
So when you combine billions of hosts, millions of intermediary routers and switches, and this massive global web of copper, glass, and radio waves, the sheer complexity is just staggering.
It's a miracle it works at all, honestly.
Right. Which brings up a great question. How do network engineers actually conceptualize and manage this matrix without getting hopelessly lost?
Well, they use specific topology maps, but they have to split their perspective into 2 distinct views: the physical topology and the logical topology.
Okay, so what's the difference?
The distinction is absolutely critical, especially during an outage. The physical topology map is concerned exclusively with the tangible layout.
Like where things actually are.
Exactly. It details exactly which server rack a device is bolted into, what specific wall port a cable runs to, and the physical pathways of the conduit in the ceiling.
So it's essential for the technicians who are physically installing or replacing the hardware.
Exactly.
But if I'm a network engineer remotely troubleshooting a routing loop or a blocked connection from 3 states away, a map of where the cables physically sit in a wall doesn't help me at all.
Nope, it's useless to you.
It doesn't tell me why the data is failing to reach its destination. I need the logical topology map.
Yes, the logical view strips away all that physical geography and focuses entirely on the flow of data.
Right, it maps out the IP addressing schemes, the subnets, the virtual interfaces.
Exactly. It shows how the devices relate to each other structurally, regardless of whether they're sitting in the exact same room or separated by an ocean.
And speaking of distance, that geographic separation dictates another major architectural boundary, right? The difference between a LAN and a WAN.
Yeah, that's a huge distinction. A local area network, or LAN, is an infrastructure that spans a small geographical area, like a home or a single office building.
Okay.
And because it is highly localized and typically owned and managed by a single organization, it is economically feasible to provision extremely high bandwidth, often gigabit or even multi-gigabit speeds, between those internal devices.
But a wide area network, or WAN, bridges the gap between those isolated LANs over vast geographic distances.
Right. Cities, countries, continents.
And because pulling hundreds of miles of private fiber between 2 cities is prohibitively expensive for most companies, WANs are usually managed by large telecommunications service providers.
Exactly. Organizations lease bandwidth on these provider networks, which historically meant WAN links were significantly slower and a lot more expensive per megabit than local LAN connections.
Got it. And understanding those scopes helps clarify the structural boundaries of the networks we interact with daily: the intranet, the extranet, and the internet.
Yes, and in corporate security, conflating these three environments leads to catastrophic data breaches. You have to know the difference.
I always categorize them by thinking of access control at like a high-end VIP club.
Okay, let's hear it.
So the internet is the ultra-private members-only lounge. It is a proprietary collection of LANs and WANs belonging entirely to one organization.
Right.
The routing tables, the servers, the data, it is all internally facing, accessible only to authenticated employees within that corporate perimeter.
Yep. Then the extranet opens a highly controlled, monitored doorway into that environment.
Like a temporary guest pass.
Exactly. It provides secure access to a subset of the organization's network for trusted external partners.
Oh, like a supplier.
Right. A supply chain vendor might need real-time access to an inventory database on your internal network to fulfill orders, but you explicitly restrict them from traversing into the HR or financial subnets.
That makes total sense. And then the internet is the public town square right outside the club.
Yep, completely public.
It is a decentralized worldwide mesh of interconnected LANs and WANs. No single entity owns the internet. It relies on global cooperation and adherence to standardized protocols to function.
Exactly. Which leads us to the crucial on-ramps. How do homes and businesses actually physically plug into that public square?
Right, the connection technologies.
Yeah, and they're heavily segmented by the differing demands of consumers versus enterprises.
Okay, so let's start with consumers.
For a home user, the infrastructure usually leverages existing utility lines. Cable internet utilizes the coaxial infrastructure originally laid for television, which offers a shared high-bandwidth medium.
Okay.
Then there's digital subscriber line, or DSL, which repurposes traditional copper telephone lines. But what really defines consumer DSL is that it is fundamentally asymmetrical.
Meaning the upload and download speeds are different.
Exactly. The frequency bands on the copper wire are unevenly divided. They allocate a massive chunk of the frequency spectrum to downstream traffic and a very narrow slice to upstream traffic.
But honestly, that asymmetry perfectly matches consumer behavior, right?
How so?
Well, a home user is constantly pulling heavy data down, streaming 4K video, downloading massive software updates, but they're rarely pushing heavy data back up.
That's true.
A few kilobits per second is usually enough for their outbound web requests or like online gaming inputs.
Right, but an enterprise environment flips that requirement entirely.
Oh, sure.
A business hosting its own web services or synchronizing massive offsite database backups
Yeah.
or running a centralized VPN for hundreds of remote workers, They require immense outbound
So
capacity.
asymmetrical connections would just choke under enterprise workloads.
Exactly.
Yeah.
Therefore, businesses invest in symmetrical infrastructure. They lease Metro Ethernet, which extends high-speed LAN protocols across a metropolitan area, or they deploy symmetrical business DSL, where the copper frequencies are balanced to provide identical upload and download speeds.
And they also use dedicated lease lines,
Okay.
right?
They pay a premium for a reserved private circuit that guarantees bandwidth availability 24/7, completely insulated from the congestion of shared consumer networks.
Looking at the evolution of these enterprise networks reveals one of the most profound architectural shifts in modern technology.
You're talking about convergence.
Yes, because think about it. 30 years ago, if you were wiring a new corporate headquarters, you had to build three entirely distinct physical
It is
infrastructures.
a nightmare.
You pulled one set of cables for the computer data network. You pulled a completely separate web of copper wiring solely for the PBX voice telephone system. And if you needed a closed-circuit television or broadcast video, you pulled a third isolated coaxial network. Three separate systems, each with its own proprietary hardware, its own rigid standards, and its own maintenance teams.
Right. And if we connect this to the bigger picture, the historical pain of maintaining those siloed infrastructures is exactly what drove the industry toward the converged network.
Right.
Modern architecture abandons the physical separation of services entirely. Today, data, voice, and video are multiplexed and carried together over a single, unified physical infrastructure.
It's the exact same evolutionary path as the modern smartphone.
Oh, that's a great comparison.
Right.
Yeah.
Because we used to carry a physical point-and-shoot camera, a separate digital calculator, a standalone GPS unit, and a cellular phone.
And a Walkman.
Yes. Eventually, all those discrete hardware functions converged into a single glass slab running a unified operating system. The networking world achieved the exact same elegance with its cabling and infrastructure.
And that convergence dramatically reduces capital expenditure and administrative overhead. The converged network uses a universal set of rules, protocols, and implementation standards.
So an email payload and a live voice call are digitized, chopped into data packets, and routed across the exact same physical wire using the exact same underlying logic.
Exactly. However, collapsing all those critical services onto a single infrastructure introduces a massive operational risk.
The million-dollar engineering problem. If your data, your phones, and your security cameras all ride on one converged network,
Right.
a single failure point could theoretically paralyze the entire organization.
Right. And to prevent that, the network architecture must be built upon four critical pillars of reliability.
Okay, what's the first pillar?
The first pillar is fault tolerance.
Limiting the impact of a failure.
Exactly. It's the engineering practice of designing a system that limits the blast radius when hardware inevitably fails. The core mechanism here is redundancy. Network architects eliminate single points of failure by provisioning multiple disparate physical paths between the source and the destination.
So if a core router experiences a catastrophic hardware failure or, an excavator severs a primary fiber trunk in the street,
Which happens more than you'd think.
I bet, the network automatically detects the loss of link and dynamically reroutes the traffic over an alternative path in milliseconds.
Right. And this dynamic rerouting is only possible because of the brilliance of packet switching.
Yes, I love this concept. Let me use an analogy here.
Go for it.
Imagine needing to send a highly sensitive 100-page manuscript to a publisher. In a circuit-switched traditional phone network, you'd put the whole manuscript in one truck on one dedicated highway.
Right.
If that truck crashes, the entire transmission is lost. But packet switching fundamentally changes the mechanism. It takes that manuscript, shreds it into individual paragraphs, and places each paragraph into its own uniquely numbered envelope.
Okay.
It then hands all those envelopes to the local post office, which is our router.
That's exactly how it works. The router evaluates the global network state in real time. It might send packet number 1 over a fiber link through Chicago and packet number 2 over a satellite link through Dallas, based entirely on momentary congestion.
Every single packet routes independently.
Exactly. If the Chicago fiber link drops, the remaining packets seamlessly route around the failure. When they arrive at the destination, the receiving host uses those sequence numbers you mentioned to reassemble the data.
And if a packet was lost in transit, the receiver simply requests a rapid retransmission of just that single missing piece, ensuring the application layer remains completely stable for the user.
It's incredibly resilient. Which brings us to the second pillar of a reliable architecture, scalability.
Okay.
The network must be able to expand rapidly to accommodate new users and services without degrading the performance of the existing environment.
And this scaling is achieved because the entire industry adheres to standardized protocols,
Hmm.
right?
Yes. Vendors like Cisco, Juniper, or Microsoft don't have to reinvent the fundamental language of data transmission every single time they release a product.
Right.
They build to universally accepted standards, allowing heterogeneous hardware to interoperate flawlessly as the network grows.
Okay, so that's fault tolerance and scalability. What's the third pillar?
The third pillar addresses the physical limitations of bandwidth, and that is quality of service, or QoS.
Because even on a highly scalable network, you can still have traffic jams.
Exactly. Momentary bursts of traffic can easily exceed the physical capacity of a router's interface. When demand outpaces supply, you get congestion. To handle this, network devices place the excess packets into memory buffers, essentially forming a queue.
But without QoS, that queue just operates on a strict first-come, first-served basis, right?
Right, which on a converged network, treating all traffic equally is disastrous.
I can see why. I mean, if an employee is downloading a massive software update and another employee is on a high-stakes live video conference with a client, those packets are fighting for the exact same bandwidth.
Exactly.
Yeah.
And a web download can easily tolerate a 300 millisecond delay in the buffer queue. The user won't even notice.
But if the live voice and video packets are delayed by 300 milliseconds, the audio desynchronizes, the video artifacting becomes severe, and the communication just breaks down entirely.
Exactly. So QoS solves this by actively managing the buffer queues. Administrators configure the routers with classification policies that tag specific types of traffic.
Oh, I see.
Voice and live video are tagged with high priority. When congestion occurs, the router examines those QoS tags and actively pulls the highly sensitive voice packets out of the buffer, allowing them to jump the line ahead of the less sensitive web or email traffic.
It guarantees a smooth experience for real-time applications at the expense of a negligible delay for background data. That is incredibly smart.
It really is. And finally, the fourth pillar is security.
Right, because the most fault-tolerant, scalable, and prioritized network is utterly worthless if the data payload is compromised.
Absolutely.
Yeah.
A reliable architecture demands proactive security measures baked into the design from day one, ensuring the confidentiality, integrity, and availability of the data against both external threat actors and internal vulnerabilities.
Wow. So, synthesizing all of this, the modern network really is a masterclass in engineered orchestration.
It's a marvel.
It feels so intuitive, almost magical, to just pull a high-definition video stream from a remote cloud server while you're traveling at 70 miles an hour down the highway.
Right, but beneath that seamless user experience is this intensely structured system of end hosts, intermediary routers making millions of pathing decisions a second,
Physical media leveraging electromagnetism and light.
and rigid logical rules dynamically managing priority and faults.
It really is an architecture meticulously designed to route data across the globe faultlessly and instantly. Well, thank you for joining us on this deep dive.
Thanks for having me.
As you go about your week, utilizing this converged digital infrastructure, I want to leave you with one final thought based on the physical media we discussed.
Oh, this is a good one.
We are constantly innovating new modulation techniques to push more data through copper wires and firing more complex lasers through microscopic glass to achieve these staggering bandwidths.
We are always pushing the limit.
Exactly. But physics is not a suggestion. It has absolute boundaries.
Yep.
The speed of light in a vacuum is a hard limit. So what happens to the trajectory of global networking when we finally collide with the absolute laws of physics limit for how fast an electromagnetic wave or a photon can actually travel? How will the architectures of tomorrow continue to scale our interconnected world when we mathematically cannot push the physical medium a single microsecond faster? Something to think about.